Okay, good evening, everyone. Can you all hear me? Good evening, Sai. Good evening, Shant. So, can you all hear me and also can you see my screen? Okay, thanks, Andrea. So, we'll start the last, just 1 minute. Some issue. Okay, yeah. So, we'll start the last lecture of this workshop on foundations of data science. Today we'll discuss neural networks and specifically CNNs. Okay, so CNN stands for convolutional neural networks. This was the neural network which made deep learning so popular. Okay, so this C stands for convolutional. Okay. After today's class, you'd know what this convolutional term means. So we'll see the architecture of CNNs, maybe not from a very detailed perspective, but I mean rather we'll try to understand what it does. Okay, what's the basic structure? So we'll be able to understand what this convolution means. Okay, so convolutional neural network. So, I mean, the current hype in deep learning started in 2012. Okay. When a deep learning based model, specifically a model called AlexNet, which was a CNN based model. Okay. So, AlexNet was a CNN based model, which, I mean, this model won a famous championship called ImageNet Championship. Okay, this was a challenge. Okay, this was an international challenge where I mean all the machine learning participants, I mean they came with their own models so as to identify images. Okay, so I mean you were given a certain image. Okay, and you had to tell what the image is. Okay, I mean there were like 1,000 different things. Okay, say cats, dogs, fish, chair, table, pastry, okay, car, motorcycle, and so on. Okay, there were like 1,000 different things. Your objective was to somehow learn a model. Okay, so you were given about 1 million images, and somehow you had to train your model, learn a model which would then I mean which then was used to make predictions on some other query points. Okay, new query points which were not shown to you during the training time. Okay, and this in 2000, I think it started in 2009 or 10, I think in 9. Okay, but during the initial few years non deep learning based models were performing the best. Okay, but in 2012 the first deep learning based model, AlexNet, won by a great margin. Okay, by a huge margin. And thereafter, since 2012, I think this championship ended in 2017 or something. I think, I'm not, again, not sure. But after 2012 it was, I mean, constantly won by a deep learning based model. Okay, so that's sort of the reason behind this huge boom of deep learning. Okay, this recent boom, I mean, if you go back and trace the history of deep learning, there were like three such booms. Okay, so the first boom was around, I think, after 1950. So starting 1950s. Okay, so starting 1950s there was this boom in deep learning. Okay, and I think in 1969 there was a sort of a winter. Okay, so everybody stopped working in deep learning since 1969. Okay, there was this, again, a seminal paper by Minsky and Papard, which showed that deep learning models are not so powerful. Okay, in a certain sense. Okay, then I mean people stopped working in deep learning for quite some time. Then again a momentum started in around 1980s, late part of 1980s, specifically 1987, when again another seminal paper on back propagation. Okay, so if you have seen deep learning, you might know what I'm talking about. If not, then just forget about it. Okay, so this back propagation paper was published, and again a lot of people started paying attention to deep learning. Then in the first part of 1990s, okay, until maybe 1997 and 98, I mean, people paid a lot of attention to deep learning. But then again there was a winter. Okay, and then again since 2012 this recent boom in deep learning started, and we are still in the uphill process of using deep learning. Okay, so it's still a boom. It has not died down yet. Okay, the craze of deep learning. Okay, so today our objective would be to somehow at least qualitatively appreciate the architecture of deep learning. Okay, and then specifically see CNNs, one specific kind of deep learning model, okay, convolutional neural networks, which are specifically used for images. Okay, so CNN is specifically used for image tasks, okay, tasks related to images. Okay, and we'll specifically probably look at digit recognition. Okay, digit recognition, where you would be given the image of a digit, handwritten digit, and your objective is to somehow recognize the digit, okay, the digit that is given to you. Towards that, I'll briefly let me show you the images and all. We'll learn the CNN model. Maybe we'll come back and see some parts of the code later. But this is what you get. Okay, these are some of the handwritten digits. Okay, the images of some handwritten digits. Okay, so the first digit is 4. Okay, the second digit is 1. The third digit is 7, and so on and so forth. Okay, so these are like images. Okay, images of handwritten digits, and you have the corresponding true digits here. Okay, so this is like 4, this is 1, this is 7. Okay, so here you are given the labels. Okay, the labels are given to you. Okay, again, recall our division into supervised, unsupervised, and reinforcement learning. Right here also you have input. Your input are these pixels. I hope everybody knows what a pixel is. A pixel is a constituent of an image. Okay, so images are built by joining pixels. Okay, so if you see carefully, I'm pointing to one pixel. Okay, so this box, this square box that you see, this is one pixel. Okay, it has a certain value. Okay, so this particular image has, I think, 28 by 28 pixels. Okay, so 28 pixels in rows and 28 pixels in the columns. Okay, a total of 28 into 28, which is, I think, 784. So there are 784 pixels in this particular image. Okay, that's your input. Okay, your input is this image. Your output is the corresponding class label. Okay, this 4. So your job, okay, by your job I mean the model's job, is to predict the class, the digit, given this image. Okay, so given this image, your objective is to make prediction about this class. Okay, and we build a model based on CNN, blah blah blah. Okay, and let me just show you the final output. So this is an image for which we do not know the actual class. We do not know what digit it is. Okay, and it's our job to make the prediction. I mean, for us it's quite easy actually. I mean, this is 6 obviously, right? But somehow we have to let our model decide, right? We have to automate this process. Okay, and the model actually makes the correct prediction. Okay, so this is the prediction about this image. It makes the prediction of 6, which is actually the correct prediction. This is indeed the digit 6. Okay, so we build a CNN based model, okay, and train it somewhere here. Okay, this is like the learning process. Okay, here the learning process is happening, and finally we have a model which makes these predictions. Given an image, it will tell you what the digit is. Okay, so okay, so let me pause here. Are there any questions on the task? We'll see this task maybe a bit more in detail. How does a CNN architecture accomplish or build such a model? Before that, we'll also briefly look at deep learning based models. Okay, so as to understand what is a deep learning based model, then we'll move to CNNs. Okay, that's the objective for today's class. But before we move to that, does anybody have any questions? Okay, so I don't see any questions. So then let me unshare my laptop screen and let me move to my iPad and we'll start writing. Okay, so yep, let me pull up the chat on my laptop. Yep, all good to go. Okay, so deep learning. Okay, so I had already told you that deep learning is, I mean, it's a part of machine learning, right? I hope you all recall this diagram where you have AI, right? You have AI, then inside that you have ML, okay, and inside that you have DL, okay, deep learning. So deep learning based architectures are again machine learning architectures. Okay, these models also learned from experience, from data. They learn from data. Okay, but they have a specific structure. The structure is that of a artificial neural network. Okay, that's a defining thing about deep learning. They're again machine learning based models, but the architecture that they follow is the architecture of an artificial neural network. Okay, again, this artificial neural network is heavily inspired from the architecture of a neuron in our brain. So I think I showed you this diagram previously. So this is a typical neuron inside your brain. Okay, your brain has about some 100 billion such neurons. Okay, all of them connecting with one another, and they send information to one another. Okay, and there are like some trillions of connections. Sorry, 100 trillions of connections. Okay, so I mean, when I say connection, it means that there is another neuron here. Okay, there is another neuron here, and that neuron somehow passes information to this. Okay, another neuron passes information to this. Okay, and so on. Okay, and then this neuron also passes information to the next neuron, and so on. So everybody passes information, and that's how communication and decision making happens. Okay, so information is stored in these connections. Okay, that's how this entire process works. Now the objective in deep learning is to somehow mimic this architecture, okay, into a computer. That's the objective. Okay, and therefore for a neuron, okay, we have, I mean, instead of this architecture, okay, of a biological neuron, we have this architecture of an artificial neuron. Okay, where again this circle that you see, this is the neuron. Okay, it receives certain inputs. Okay, just like a neuron receives certain inputs. Okay, so I mean, this part of the neuron is actually called an axon. Okay, and these are called the dendrites. Okay, so it receives dendrites. I hope the spelling is correct. Okay, so it receives certain information through its axons. Okay, similarly, this neuron also receives certain information. Okay, x1, x2, x3 up till xd. Okay, it does some computation here and spits out something. Okay, just like this neuron also does some computation and spits out information out of its dendrites. Similarly, this neuron also receives certain information, does some computation, and spits out something. Is this architecture clear? Or does anybody want me to repeat the architecture, the details of the architecture? This is the neuron. Okay, it receives certain inputs, does some computation here. We'll see the computation. Okay, I mean, I have not told you what computation it does yet, but we'll see that. Okay, and spits out something, some y hat. It spits out some y hat. Okay, that's like the basic computing unit. This is one single artificial neuron, right? Later on, we'll stack neurons one on top of another. Okay, so everybody would pass information. So the first neuron would pass information to the next neuron. The next neuron would pass information to the next neuron, and so on. Okay, and we'll construct an entire architecture. Okay, a network of such neurons. That's what an artificial neural network is. Okay, when you connect neurons with one another and each neuron passes information to the subsequent neuron, we call that architecture an artificial neural network. Okay, but this is one such neuron. Okay, now let's just see what computation it does. Okay, the computation is very simple. What it does is, suppose it receives x1, x2 up till xd. Okay, this information. Okay, so it receives x1, x2, x3, x4, x5 up till xd. Okay, d is some number. Okay, maybe d is 10. Okay, we are just putting d so as to mean that it could be any number. Okay, so this is like the dimension of the input. Okay, that's why d. Okay, so if it's like 10 dimensional information, it will have x1, x2, x3 up till x10. Okay, and correspondingly you will have w1, w2, w3 up till w10. Okay, they could also be 100. Okay, just so as to make this entire thing general. Okay, general enough so that it can receive any number of inputs. We are putting a d here. Okay, so the computation is very simple. What it does is, let me write down the computation. So this is y hat. Okay, this is the final output. Okay, so the y hat would be computed somehow. Okay, how is it computed? So first you do w1 x1, okay, plus w2 x2 plus W3 X3. I hope you get the idea. Up till WD XD. Okay. This is the computation. So this is like a linear sum. Okay. So W1 X1 plus W2 X2 plus W3 X3. Okay. Up till WD XD. So what you're doing is you're multiplying each of the inputs with their corresponding weight. This W stands for weight. Okay, so every input is multiplied with a corresponding weight. What these weights are, that's a separate question. Again, we'll try to answer that later on. Okay, but now just understand what is happening. Okay, not why are we doing this? Okay, so first you take x1 multiplied with w1, then you take x2 multiplied with w2, and so on, and then finally you add all of them. Okay, and finally you have a w naught. Okay, so maybe let me just erase this and make this w naught. Okay, so just add w naught. There's no x naught. Okay, so just add w naught. Okay, this is the computation. Okay, let's just see this computation for d is equals to 1. Okay, when you have only x1, that's it. Okay, x1 and w1. In that case, y hat would be what? w1 x1 plus w naught. That's it. Okay, does anybody remember this? Does anybody remember this term? Did we see this in any of our previous lectures? W1 into x1 plus w naught, or maybe a w into x. Okay, because there's only one. So w into x plus w naught. Y is equals to mx plus c. Exactly, right? We saw this yesterday, right? This is nothing but a line, right? Where this w is the slope and this w naught was the intercept, right? This is exactly the equation of a line. Somehow what we're doing here is we're generalizing it beyond one dimension. Okay, here you have only one dimension, x. Okay, here you have x1, x2, x3, and so on, right? So you have here you have only one dimension or one direction. Okay, so let me just put one again. Okay, so you have only x1, so correspondingly you have the slope along x1, which is w1. Okay, but now if you have more number of dimensions, okay, x1, x2, x3, and so on, and I mean in machine learning tasks, usually you have many inputs. Okay, so this x1 is like one input, maybe somebody's name. Okay, x2 might be somebody's salary, x3 might be somebody's date of birth. Okay, x4 might be his marital status. Okay, and so on. So you have many inputs. It's not like you always work with a single input, right? So somehow you have to generalize beyond a single input. Working just with x1 doesn't make sense. Okay, so we have to work with x1 to xd. We have to make it general enough. Okay, and therefore will not have one slope, will have multiple slopes. Okay, just like for x1 we had the slope w1. Okay, so similarly here also I'll have w1 slope for x1, w2 as slope for x2, w3 as slope for x3, and so on. So this is nothing but again an equation of a line, but the line is in very high dimensions. It's in d-dimensional space. Okay. Okay. So we saw the line in 2 dimensions. Okay. So x and y, right? We saw a line. Okay. The slope of the line was w1. The intercept was w naught, right? Now you can try and imagine this thing in 3 dimensions. Okay. It's a bit difficult to draw 3 dimensions on paper, but I can still try and make you imagine it. Okay, so this is like a 3-dimensional plane. Okay, so x, y, z. Okay, something like this. Okay, I mean just imagine z, the z axis, to be coming out of your screen. Okay, and this is the 3-dimensional axis. Okay, I can still make you visualize 3 dimensions. Okay, but beyond 3 dimensions it's not possible for us to visualize, right? You can't imagine a 4-dimensional space or a 5-dimensional space. Okay, that's not possible, so we don't even try to do that. Okay, but we just try to imagine a 3-dimensional space and just scream, it's a d-dimensional space. That's it. Okay, so this line, this is again a line. Okay, intercept plus this slope into the dimension. Okay, it's exactly in the form of a line, but the line is in a very high dimensional space. It's in a d-dimensional space. If d is 10, then it's a line in 10-dimensional space. Okay, so this computation is a linear computation. That's the point. Okay, Recall that yesterday we told ourselves that linear means a line. Okay, so here also we are doing a linear computation of all the inputs. It's a linear combination of all the inputs. Fine. Any questions up till this part? So let me erase all of this. Okay, and this is the final computation. Okay. Any questions until this part, or do you want me to repeat any part? Okay. So the next thing is, just a linear computation is actually not powerful enough. Okay, I haven't discussed this point, but this is again a very important point in machine learning, that linear models are not so powerful models. Okay, they won't be able to do a lot of things, right? So what we do is, on top of this linear model, we put something non-linear. Okay, so this neuron has two parts. This neuron has two parts. It does two computations. Okay, the first part is linear, which is what we wrote. Okay, and the second part is non-linear. Okay, we already discussed, we touched upon this idea yesterday, that if you have a data set, I told you that we were fitting a line, right? If you have data points like this, you were fitting a line, right? But you can imagine that fitting a line always does not make sense. A line is a very restrictive kind of model, right? If I have data points like this, okay, you can imagine a data set which is like this, right? In that case, fitting a line does not make sense. Fitting a parabola makes sense. And parabola is not a linear function. Okay, it's not a linear model. It's a non-linear model, right? So in many situations, you need to go beyond lines, beyond linear computations. So here also, what we will do is we will go beyond linear computations. Okay, so first we will linearly combine the inputs. We won't call it y hat. We will call it z. Okay, z, which is like an intermediate computation, right? And then we will pass this z through some non-linear function. Okay, and then we will get y hat. Okay, so where this f of z, this is a non-linear function, non-linear, and this function has actually a name. Okay, it's called an activation function. Okay, there are reasons for calling it an activation function, but we won't go into those things at least in this lecture. Okay, but the point is, linear is not always sufficiently powerful model, right? So that's why we first do linear computation. It's like an intermediate computation of z here. Okay, and then we pass the z through some non-linear function, so that now the entire output is like a non-linear thing. Okay, so this is what my y hat is. Okay, so in short, what is a computation that a neuron does, that an artificial neuron does? It combines all the inputs, okay, multiplying them with some slopes. These slopes are also sometimes called weights. Okay, that's why the term W. Okay, these are also sometimes called weights. Okay, so it does a weighted combination of the inputs and then passes this combination through a nonlinear activation function and spits it out. Okay, is this clear? Does anybody have any question? Okay, so if this is fine, then now comes the network part. Okay, this is like one neuron, but obviously one neuron is again not powerful enough. We'll have to, create or have multiple neurons connected with one another who share information, who pass information to one another, just like our brains do. Okay, so towards that, we have something called a deep neural network. Okay, or multi-layered neural network. Okay, where this is a neuron. Okay, this is one such neuron. Okay, just like this neuron. Okay, so instead of this one neuron, you have multiple such neurons here. Okay, four such neurons here, and this neuron receives input. Okay, receives information from these three: x1, x2, x3. Okay, so these three here. Okay, these are not neurons. Okay, these are just inputs. Okay, this is x1, this is x2, this is x3. Okay, this neuron also receives information. Okay, everybody receives information. They do the computation, spit out something, and pass it to the next neuron. Okay, this neuron again receives information from this neuron, this neuron, this neuron, and this neuron. Okay, This is what a neural network is. Again, I mean, you might get confused by seeing all of these things. Okay, these are just like nomenclature. Okay, naming. How do you name weights? Obviously, when you have multiple neurons, naming becomes a bit difficult. Okay, I mean, it's not conceptually difficult. It's just tediously writing all of these things. Okay, you have to make sure that you number them properly. Okay, it's just a tedious business. So we'll just ignore all of that part. The point is, every neuron does this computation. Again, see, I have two computations here. This part linearly combines x1, x2, x3. Okay. And then this part passes it through some nonlinear activation function. Okay. And spits it out to the next neuron. Similarly, this neuron also does a similar computation. Okay. And spits it out. Okay. This neuron also does a similar computation, spits it out. This neuron also does a similar computation, spits it out. Okay. Now, the point is, I mean, aren't all the neurons doing the same thing? Then why do we have multiple neurons? It seems like all of them are doing a similar kind of a thing. Then what is the point of having multiple neurons? The point is, all neurons are structurally, maybe they're similar, but they have different weights. Okay, they have different weights. Recall that Karthik is saying for the model to be more accurate. Yeah, no, I'm just saying that all the neurons are like doing the same thing, right? So why have multiple neurons? Okay, the point is that they may be structurally same, but the weights, okay, that define the neuron, they might be different, right? Recall, okay, the most important point here is that when you make some prediction y hat here, right? At the end of the day, you go back and you tried to find the best choice of W and W naught, right? Recall that yesterday we defined an error function, a loss function, okay? And we were trying to find the best choice of W and W naught. Here also, these W1, W2, W3 up to WD, these are not fixed. These are learned. Okay, this is where the learning happens. That's why the name machine learning or deep learning. What do you learn at the end of the day? You learn these weights. Okay, W0, WD, WD minus 1 up till W1. You learn these weights. Which choice of weights, okay, reduces the error most? Again, you define a loss function or an error function, just as we defined yesterday. Okay, but at the end of the day, your final objective is to come up with a choice of weights, okay, which reduces the error the most. Okay, so here also, if you see carefully, this neuron, okay, when this neuron is doing its computation, okay, it receives input from x1, x2, x3, okay, through these weights. Okay, this weight, the weight that I'm showing you, okay, this weight, okay, and this weight, these three weights. Okay, now these three weights might be different from this weight, and this weight, right? So although structurally they seem to do the same thing, but the weights might be different. Okay, and your objective at the end of the day, the objective in machine learning or in deep learning is to find the best choice of weights. Okay, here as well as here. Okay, so a deep learning model would have many weights. Okay, many layers. This is a two-layered network. Okay, this is not a layer, this is just the input. So this is like layer 0. Okay, this is the first layer. It's also called the hidden layer, and this is the output layer. Okay, but this is a very simple model. These days, many of these deep learning models have about 100 layers, okay, or 150 layers. Okay, so 0th layer, 1 layer, 2 layer, 3 layer, up till 150 layers. Okay, so you can imagine that these layers have many weights. Okay, they might have many weights in between. Okay, and the objective of deep learning is to somehow learn these weights. Fine, is this making sense? So I hope now you have a brief idea of what happens in deep learning. Okay, I mean, my objective here was to somehow open this black box of deep learning and tell you how it learns. Okay, what does it learn? It learns these weights and weights of the model so as to reduce the error. Okay, error in prediction. At the end of the day, you care about predicting something, right? Okay, so let me pause here. We discussed a lot of things. Okay, so if you have any questions, if you want me to repeat any part, please do tell me. Else we'll move forward now with CNNs. Okay, a specific kind of a deep learning model, which is a sort of designed keeping in mind the structure of the problem. Okay, so CNNs are specifically designed for images, tasks pertaining or relating to images. Okay, so it has a special structure. Again, the ideas remain same. Okay, you have weights, okay, that you want to learn at the end of the day so as to decrease your prediction error, okay, or your loss. But the structure is a bit different. Okay, it caters to the fact that the input is now an image. Okay, it's not like a random input, it's like an image. Images have structures, right? Obviously an image has structure, so I mean it tries to exploit that structure. That's what's a novel about CNNs. But again, let me pause here and take any questions if you have any, or if you want me to repeat any part, please do tell me. Okay, so I guess everything is fine. Give me a moment. Yeah, either you all are extremely intelligent, or I'm teaching extremely well, that you have understood the entire thing in one go. Okay. Okay, so then let's move ahead. Okay, now we'll talk about images. Okay, we'll first discuss maybe a few tasks in images. Sandhya Singh, can you explain formula again? Sure, sure. This formula, right? I guess this formula. So here what we are doing, we have two things here. Okay, this particular neuron does two things. There is a linear computation. On top of it, there is a non-linear computation. Okay. Why two things? Because we know that linear computation is not powerful enough often. Okay, so lines may not be powerful enough. You might want to fit something more powerful than a line, right? We discussed this point yesterday also, right? So the first part is a line. This is nothing but a line in higher dimensions. Okay, so in lower dimensions, in when you have only one dimension, okay, then a line is just w1 x1 plus w0. That's it. Okay, this is the slope along x1 and this is the intercept. Okay, but when you move to higher dimensions, if you have say two dimensions, okay, then your line would be w1 x1 plus w2 x2 plus w0. Okay, this is like a line in two dimensions. Okay, and if you go to d dimensions, this is the equation of a line. Okay, and then you pass this linear combination through a nonlinear activation function. So they're saying, can you formula in two-layered network? Oh, these formulae. No, I didn't discuss this. Okay, I have just written it down, but I didn't discuss it. Okay, maybe it might have been prudent not to write this. I mean, it's the same thing. Okay, again, if you see carefully, this is what w into x. Okay, this is a summation. So again, this is like w1 x1 plus w2 x2 plus w3 x3. Okay, and this b1 is nothing but w0. Okay, so it's a similar kind of a thing. Okay, but I didn't discuss this because it's like just keeping track of the numbers. Okay, it's just painful numbering. That's it. Okay, the idea still remains same. Okay, so you don't need to pay attention to the formula. Just pay attention to what it does. This linearly combines x1, x2, x3. This again linearly combines x1, x2, x3. Okay, so does this neuron and so does this neuron. Okay, finally you pass all of this through nonlinear activation in the second part of the neuron. That's it. It's the same thing what a single neuron does. Now, I mean, while writing it, you just have to take care of the notation a bit. Okay, the notation becomes a bit messy. So we have sort of a fixed nomenclature that everybody in the deep learning community follows. That's it. Okay. Okay. So now the next thing is about image classification, where this is a specific task, okay, in images where your objective is to classify an image. Okay, classify an image into one of many possible classes. Okay, so for example, here this image is that of a dog. Okay, so you have to come up with the prediction dog if your model sees this image. Okay, and this image data set that I talked about, this was the challenge. I mean, this was a challenge which was started in 2009, and in 2012 a deep learning based model beat all other machine learning based models. Okay, in this challenge, here you had about 1,000 different classes. Okay, and about if I remember it correctly, about 1.5 million images were given to you. Okay, and your objective was to somehow learn about learn to predict, make these predictions. Okay, so there were 1,000 different classes. Some of these classes were like, fish, furniture, food, dog, maybe cat, spiders, and so on. Okay, so you had 1,000 different categories, and your model had to learn to make predictions into one of these 1,000 different categories. Okay, that was the objective of this particular image data set. Okay, so this is the image classification task. Okay, image data set was for image classification, but you also have some other problems. I just know, I'm just talking about two problems in images. Okay, but there are like many problems these days. Okay, many tasks. The second problem is a bit more difficult than image classification. Here you want to not only classify an image, okay, but also put a bounding box. So you have to detect an object. Okay, for example, in this image, okay, the model is detecting that there is a laptop here. Okay, so first there is a classification into laptop. Okay, then it is also putting a box, a bounding box around it. So it's two things. Okay, first you have to classify, then also you have to localize where is the laptop present. Okay, so this is the task of object detection. It's slightly more difficult than image classification. Okay, then there's this uh, another object called bottle here. Okay, then another object called cup here, then bowl here, handbag here, mouse here, and so on. Okay, so your objective is to somehow detect all of these objects. Okay, for this also you can use a CNN based model. Okay, but we won't be able to discuss such an architecture now, at least. Okay, but let's try to at least understand what does a CNN do. Okay, what does a CNN do? The first thing is CNN stands for okay, I didn't write it. So CNN stands for convolutional neural network. So the neural network part is, I hope, clear to everybody. All we need to understand is what is this convolutional operation. Okay, this is a specific operation, and we'll understand what it does. Okay, so but before we go there, let me just talk about images in general. So any image in your computer is represented as pixels. Okay, so it's like these are like boxes. Okay, so every image is composed of many such small boxes. Okay, each box is like one pixel, and each pixel has a number. Okay, each of these pixels has a number between 0 to 255. Okay, let's just talk about black and white images for the time being. Okay, we'll talk about colored images later. But if the image is black and white image, okay, a grayscale image, then 0 represents black, 255 represents white, complete black and complete white, and between 0 to 255 you have a transition. Okay, one is slightly less black, two is even lighter black, and so on, right? So you understand that there are different shades of gray from 0 to 255. Okay, 0 is complete black, 255 is complete white, and in between you have a slow transition from black to white. Okay, a grayscale image. So that's how you represent your image. Okay, each pixel has a number. Okay, if the number is 0, then this pixel would be completely black. If you have a 255 here, then this particular pixel would be completely white, and so on. Okay, so when I write this, okay, this is like an image. Okay, this seems like a matrix. Okay, but this matrix is nothing but an image which has 6 by 6 pixels, and I've written some random numbers. Okay, so this is like 5, 7, 1, 2, 3, 9. Okay, so these are like random numbers. Okay, the numbers of the pixels. And now I'll tell you what the convolutional operation does. Okay, first again we'll try to understand what it does. Later on we'll try to understand why it does. Okay, why it does whatever it does. Okay, so first let's understand what does it do. What does the convolutional operation do? Okay, so the convolutional operation is a simple enough operation. It first has something called a filter. Okay, this is a filter. You pick up this filter, you put it on the image. Okay, like this, and then you multiply and sum. That's what you do. Okay, how do you multiply and sum? So you take, say, you take this pixel multiplied with this pixel. Okay, so 5 into 1. Okay, 5 into 1 plus 7 into 0 7 into 0 plus 1 into minus 1. Okay. Now, next 8 into 1. 8 into 1 plus 6 into 0. 6 into 0 plus 2 into minus 1. 2 into minus 1. So I hope you have got the idea what I'm doing here, right? Then you take this, multiply it with this, take this, multiply it with this, take this, multiply it with this. And whatever you get, you write that number here. Okay. If you go back and do this computation, you'll find that it's 9. Okay. You write that number here, right? Is this computation clear? That you pick up this filter, place it here, right? And then multiply the overlapping pixels and sum all of them up. This is the convolutional operation. Again, just pay attention to what it does, okay? Not the why question. Why the hell are we doing this crazy computation? That's a separate question. We'll try to answer that question later on, okay? But first, just understand what is it trying to do. Is this clear? Does anybody want me to repeat the computation? Okay, so I guess everything is fine. So this computation, then what it does is it shifts this filter one step, okay? And again does the same computation, a similar kind of a computation. Again, multiply the, how to select the filter. That's a very, very, very good question, okay? But again, we'll try to answer that question later, okay? That's a very good question. We'll come to that, okay? How to select the filter, okay? It's a very important question. We'll answer that question, okay? But for now, just understand what it does, okay? It has some filter, it has some image, okay? It's doing some crazy computation. We don't know why. We'll try to understand, okay? Then it shifts this filter by one step and again does the computation, a similar computation, and it again finds that the number is say 5, okay? And it puts a number here, right? Then it will take the filter, it was here, then again shift it by one step. Again do the same computation and put the number here, okay? And so on, okay? Once it is done with, within the row, okay, then it will shift by one row, it will come down, okay? And then again go like this, okay? Then again it will come down here, again go like this, okay? Then again come down and go like this. So this filter would travel throughout the entire image and do this convolutional operation. Fine. Okay. All right. Now let's try and understand why is it trying to do this, crazy computation. First, let me erase some part. Okay. First, let me ask you, can you tell me how would this image look like? Can you try to visualize this image for me, right? I already told you that 0 is like complete black, 255 is like complete white, okay? And then in between you have different levels of gray, right? So now can you describe this image to me in English? How would this image look like based on these pixel values? Can you describe this image? How would this image look like? Sandhya is saying 1. Shant is saying right half image looks black. The right half is black. What about the left half? That's a correct observation, right? The right half is completely 0. So it's like completely black. Correct? This part should be completely black. What about this part? The left half? 50. 50 is like gray. Correct? So half of the image should be gray and half of the image should be black. Okay? So half of the image is gray. Okay? And half of the image is black. Fine? This is what the image should look like. I hope you can, I hope you can correlate this, these numbers to this image. Okay. And now if I do convolution with this filter, okay, again, you can go back and do this computation. Okay. It's that crazy computation that we did above. Okay. You'll find this image. Okay. You'll find this image. Okay. And again, what does this image look like? It's like black here, black here, black. Okay. And then in between you have gray. So this is the computation. Okay. And now, if you see carefully, what is it trying to find? Okay. I mean, this is a toyish example, so the image is not so big, right? But if you have a very big image, if you have a very big image, it is finding something here, right? I mean, the remaining part, if the images would have been very big, right, then there would be a lot of zeros here, okay? A lot of zeros on the other side, okay? A lot of zeros on the left side, a lot of zeros on the right side. And in between, you'll have 2 pixels, okay? A very thin white line, okay? So it has found something from this image. Can you tell me what has it found here? It has found something in the middle part of the image. Can you tell me what has it found? What's there in the middle part of the image? There is an edge in the middle part of the image. This is nothing but an edge, right? I hope you see this, that there is an edge here, okay? A transition from gray to black, okay? So this particular filter has somehow detected, yeah, a separation, okay? A separation or an edge, a transition of color, okay? So this particular filter has detected an edge, okay? A vertical edge, okay? And in fact, this filter is actually called a vertical edge detector. That's why this filter, okay? That's the reason why we chose this filter. It's a vertical edge detector. Now you might ask me, how did you come up with this? Well, creativity. I didn't come up with this. Some people in digital image processing came up with this a long time ago. Okay. Maybe before even your parents were born. I mean, digital image processing is quite an old subject, and these edge detectors were, I mean, they were around in the literature, maybe starting from 1950s or something like that. Okay. So this is a specific kind of an edge detector. It's a vertical edge detector. Okay. And now if you sort of try to imagine, can you tell me what would this detect? What would this detect? This filter detect? And just compare this filter with this filter. If the first filter is a vertical edge detector, can you tell me what would this filter detect? Horizontal edge, right? It seems, yeah. So everybody sees this, right? It should detect a horizontal edge, right? So this is again a horizontal edge detector. Okay. Yeah, all of you see this, right? So this is actually a horizontal edge detector. And now again, you should step back and think, why do we care about edges and all, right? We care about edges because classification often depends on such features. Okay, this is one feature. Is there an edge? Where is the edge? Okay, now let's go back to our task. Okay, our task was to identify a digit, right? A handwritten digit, right? Now you immediately see that if I somehow know that there is a horizontal edge in the middle part of the image, most likely this digit is 7, right? No other digit has a horizontal edge in the middle, correct? So somehow if I can detect this feature, that there is a horizontal edge in the middle part of the image, I know that this should be, I should make a prediction of 7, right? Our brains also do such computations. Okay, it's just that we are not aware of such things. Okay, but our brains also have edge detectors and change of contrast, change of color detectors, and so on and so forth. Okay, so here also, if somehow we detect an edge in the middle, we are done, right? We are done that, and we can go ahead and say that this is a 7, right? So I mean, having such features from images is a very important part of making predictions. That's why we care about such features. Okay, it's one feature. I agree that, I mean, it might not be enough. Okay, you might, maybe you would like to look at corners. Okay, you might want to look at change in color, change in brightness, change in perspective, change in contrast, blah blah blah. A lot of features. Okay, okay, that's why what people do is they put in a lot of feature detectors. Okay, these filters are also sometimes called feature detectors. They detect certain features. Okay, okay, is this making sense? Why are we doing this convolutional operation with a filter? Because filters are feature detectors which detect features in the image. Now, what do you do with these features? Features help you in making predictions about the image. That's why we care about detecting features. Is this making sense to all of you? Why this crazy computation of convolution? Okay. Now, the next interesting question was, I think somebody had asked, I forgot who, that how do I come up with this filter? Okay. So people were trying to come up with better and better filters, okay, better and better detectors. Okay. So somebody came and said, so I mean, precisely to be precise, Sobel, he was again a computer scientist who came up with his own filter. He said that use this filter, okay, use my filter, okay, this is a better edge detector. Shar, another computer scientist, came and told that, okay, no, my filter is even better. Okay, if you use my filter, it's even better. Okay, and there was no principled way of checking whose filter is better. Okay, what you could do was to check this empirically. Okay, go ahead and use these filters in images and see how good are the edges. Okay, that are detected by these filters. Okay, so I mean everybody was coming up with their own filters. Okay, but I mean there was no principled way of sort of coming up with these filters. These were like ad hocs. Okay, I mean people were creative, they were coming up with some filters. Okay, what CNN suggested, and this is like the fundamental part of again deep learning. Okay, and this convolutional neural networks is that, I mean, okay, Sobal is saying something, Shar is saying something, okay, somebody else is saying something. I won't sort of believe anybody. What I'll do is I'll learn the filter. Okay, instead of working with a fixed filter, what CNN does is it learns these filters. Okay, so instead of putting some numbers here, specific numbers like 1 0 minus 1 2 0 minus 2, what it does is it puts some weights, w1 w2 w3 w4 w5 w6 and so on. And at the end of the day, recall, the weights are always learned in a deep learning based model. You have to learn. How do I learn these? So as to minimize my prediction error. Right, I have an objective at the end of the day. I have to somehow make correct predictions. I have to minimize the error. Right, now you need to find filters which minimize the error. So this is the learning process. Instead of coming up with handcrafted filters, what you do is you let the model decide its own filters. Okay, I let the model choose whichever edge, whichever detector it feels is good for this particular task and this particular image. It will learn that particular filter. Okay, and this is the crux of CNNs. Okay, and this layer is called a CNN layer, convolutional layer. Fine. So let me pause here. Does anybody have any question? I think I have answered some of the previous questions. How do I come up with such filters? So this was the problem. Okay, so this was the problem. How do you come up with filters? Okay, and people for a long time were using such handcrafted filters. Okay, so some engineers would sit down and handcraft these filters and come up with some features from the image, and then that those features were used in the machine learning process. Okay, what CNN did, and this was like a revolutionary thing, was that it sort of stitched this feature detection part with the learning process. Feature detection was not done by human beings. Okay, by designing filters. Okay, it was stitched along with the learning process. So the model now decided for itself which filter was good, which filter was not good. Okay. All right, so let me pause here. If there are any questions, I'll take those questions. If not, then I'll move ahead and I'll again give you a brief architecture of CNN and then we'll stop. Okay, so it will take me about 5-10 minutes to give you the complete architecture of CNN. So, but this is the key component of any CNN architecture. Okay, this convolutional layer where you learn the filters. Okay, so I mean, if you are working with colored images, okay, so colored images in computer are represented using 3 channels. Okay, has anybody heard of this RBG channel, red, blue, green? So this is how you represent colored images in your computer. Okay, so for grayscale images you have only one channel. Okay, it's like one channel. I told you that this matrix has numbers. Okay, and you put the numbers, and according to these numbers you have a grayscale image. 0 would be black, 255 would be white, and in between you have grayscale. Right, But now, how do you represent colored images? For that, you have three channels: the red channel, the blue channel, and the green channel. And by mixing these numbers, you come up with different colors. Okay. So now you have multiple channels. Okay. So now your filters should also have multiple channels. This is called convolution on volumes. Okay. So again, the process remains same. You take up the filter and put it here. Okay. Align it with the different volumes also. Again, do the same computation and put the number here. Okay. Again, you move this particular filter by one step. Okay. Do the computation and put the number here, and so on. So the entire process remains same. Okay. Now you can, instead of putting one filter, obviously one filter would not be good enough, right? Just detecting some features with one filter is not enough, right? So but what you can do is you can have multiple filters. I'm showing you two filters here. Okay. But in general, you'd be using some 64 filters and 128 filters. Okay. You'll have multiple filters in each of these layers. Okay. And each of these filters would learn something different. Okay. Something which helps the model to make the predictions correctly. Okay. So you'll have multiple filters. Each filter would generate an image. You'll stack up that image, okay, here. And this is like your next layer. Okay. This is like your next layer. Okay. And finally, a CNN layer also has another computation, which I didn't talk about. So, I mean, it will have a convolutional layer, which we talked about in detail. Okay. It will have something called a pooling layer, which we haven't discussed. We'll discuss it briefly. It's not so interesting. And third is a fully connected layer. We have discussed fully connected layer, okay, at the beginning. So a fully connected layer is a layer like this, okay, where everybody is connected with everybody. Okay, this is a fully connected network where everybody is connected with everybody. Okay, fully connected. So everybody is connected with everybody. Okay, so any CNN architecture usually has these three types of layers. Okay, a CNN layer, which we already talked about, convolution layer, which we already talked about. Okay, then something called a pooling layer, which we will talk about now, and then a fully connected layer. Okay, so the last thing that we need to discuss before completing CNNs is pooling. So pooling is like taking maximum out. Okay, that's it. So sometimes the images that you are learning in this entire process, they might be very huge. Okay, and also you'd like to learn general features. Okay, so what you do is you take out maximum from a part of the image. Okay, from this part of the image, you take out the maximum. Okay, so what's the maximum here? The maximum is 8. Okay, so you take out 8 and write it here. Similarly, you take out the maximum from this part. The maximum here, I guess, is 9. So you take out 9 and write it here. Okay. Similarly, you take out the maximum from the third part, which is again 9 and 7. Okay. In the fourth part. Okay. So this is like taking out the most important feature. Okay, you have many features here, but you want to reduce the size of the image for computation reasons, as well as only to learn general things. Okay, the most important things. Okay, there are a lot of information here. I'm taking the most prominent information out. Okay, that's a pooling. That's a max pooling layer. Okay, so now this is how a CNN network would look like. Any typical architecture, CNN architecture, if you go back and read some of these blogs or papers, you'll find such architectures. Okay. So I just wanted you to show this architecture so that you do not get scared if you see a full CNN architecture. Okay. In some of these papers or some of these blogs. Okay. You have an image. Okay. You have a convolutional layer. Okay. The filter learning. So you have multiple filters here. You learn something. Okay. Here. Then you do max pooling. Max pooling reduces the size of the image. Okay. You have reduced the size of the image. Then you put another convolution, another set of filters. Okay. You do this repeatedly. Okay. You might do it 7-8 times. Okay. So CV max pool, again CV max pool. Okay. Then you have fully connected, and then finally the output layer. Okay. I've written some details. I mean, we haven't discussed these details, so you can ignore these parts. But what I want you to take away from this entire architecture is that in any CNN layer, it has three kinds of things. Okay, a CV layer, convolution layer, where you learn filters. Okay, that's the feature detection part. A max pool layer, which sort of finds the most important part from an image. Okay, the most important feature from an image. Okay, then it has a fully connected layer. Okay, that's it. So this is like the end of CNN architecture. Okay, so does anybody have any question at this point? We'll go back and see maybe the code briefly. Okay, so let me go back to my laptop. We'll see the code briefly. I mean, I won't discuss the code. I'll just tell you what are we doing at each of these different steps. Yeah. Okay. So here, Samil is asking what is padding. Okay, I didn't talk about padding. padding. Padding is like putting extra pixels around your image. Okay, so if this is your image, okay, you put extra pixels as your boundary. Okay, that's what padding is. Okay, it's done so as to ensure that the size of the image remains same. Okay, that's it. Okay, it's like putting a boundary around your image. Okay, so I mean, here also these are the images. Okay, these are the handwritten images, and if you see carefully, these images are constructed of pixels. Okay, so these are all the pixels. Okay, now black is like 0, so you have zeros here. Okay, and white is like 255. Okay, and then you have different shades of gray. Okay, this is like lighter gray, this is darker gray, this is even darker gray, right? So you can imagine that these would have, increasing numbers. Okay, so maybe around sorry, not increasing but decreasing. Okay, this would be like 150 maybe. Okay, this would be like 100, this would be like 50. Okay, and this is like 0. Okay, so that's how images are represented. And you have the learning process. This is the learning process where you have, convolution layer. This is the convolution layer. Okay, kernel is like filter. Okay, so what is the filter size? 3 by 3, right? We use 3 by 3 filters. Okay, then you have another convolution. This is the pooling. Okay, blah blah blah. Okay, all of these things. And this is the learning process. Okay, it takes a bit of time to learn this model. Okay, and then you have finally the model, and you use predictions. Okay, you make predictions here. Okay, you make the predictions here, and this is like the prediction. Okay, and the prediction is actually correct. Given this image, the prediction should have been 6, and it's actually 6. Okay, so that's the end of deep learning and CNN for us. I'll stop here, but if you have any questions, you can ask them. If you want me to repeat any part, you can ask me to repeat. Okay. So, I mean, we didn't discuss another architecture, which is like another family of architecture. It's called RNN, which is again very, very interesting. Okay. So, I mean, the second sort of boom was because of this architecture, RNN, which we didn't touch upon at all. Okay. But it's again a very interesting architecture. So, R here stands for recurrent neural network. Okay, and this kind of an architecture is used specifically for languages, for natural language processing. Okay, NLP. Okay, and please explain about activation function. Yeah, so I'll do. Okay, just give me some time, Manju. I'll explain about activation function. Okay, so NLP. So in NLP, what's the differing theme in NLP? Okay, so in NLP, what happens is, because you're working with languages, there is a dependence in time. Okay, what do I mean by this? Okay, for example, if I write a sentence, I play cricket, right? So I hope everybody knows that English languages have a structure, right? So this is like a subject. Okay, this is like a verb. Okay, and this is like an object. Okay, so there is a structure in English language. Okay, the next word depends on the previous words. Okay, I play, and then again another verb. That's not a structurally correct English sentence. Okay, I play, I don't know, I play sleep. Okay, that doesn't make sense. Okay, okay, or I play eat. Okay, that doesn't, that again doesn't make sense. Okay, verb followed by verb doesn't make sense. Okay, so there is a relation, a temporal relation, a relation with time. Okay, so this is like time step 1, this is time step 2, time step 3. Okay, so there is like a relationship between different time steps. Okay, that relation has to be somehow captured. Okay, and that relation is captured by an RNN. Okay, by something called a recurrent connection. Okay, if I had some more time, I would have discussed this, but I mean, we don't have enough time. So yeah, let's stop it here. Activation function. Yeah. So activation function is the nonlinear component. Okay. I mean, uh, how do I? It's a bit difficult to discuss these things without going into the details. Okay. Let me just tell you that the activation function, okay, goes from the linear part to the non-linear part. Okay. That's a job of the activation function. linear is not powerful enough often. Okay, so somehow you have to add some non-linearity to your model. Okay, so what you do is you put an activation function. One of the most common activation function is that of, is this sigmoid activation function or the logistic activation function. Okay, let me just talk about the sigmoid for briefly. Okay, what it does is the function looks something like this. Okay, it doesn't touch zero. Okay, it looks something like this. Okay, it's an S-shaped curve. Okay, this is one, this is zero, and it moves slowly towards one. Okay, this is again a non-linear function. Okay, so it gets some linear thing. It gets z, right? Recall, what does it get? Z is like w1 x1 plus blah 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 up till wd xd. Okay, then it passes it through this non-linear function. Okay, to add some non-linearity on top of it, so as to make it more powerful. Okay, so that's all, that's all I can discuss about activation functions now. Okay, discussing these things would require a lot of background, so I won't have time for that. But the main point here is to add some more modeling power. Okay, so that now it can model non-linear things also. Okay, any other questions from what we discussed? Let me do one thing. Let me stop the recording. Okay, so this won't go into uh, YouTube anymore. Okay, how do I stop the recording?